So we're showing here the intersection of a sphere, this magenta thing, centered at the magenta point, with a yellow cone. Okay, and I'm asking Mathematica to numerically compute the intersections between these two shells, and I get these two beautiful non-planar space curves, right? Topologically equivalent to circles, but they're not planar. Now what I can do with this simulation, and there's going to be some problems here, is that I can ask Mathematica to numerically report what the centroid of these two components is, and it's showing me through that blue dot. I'm showing its coordinates up here. Now the goal of the simulation was, and I haven't achieved it yet, to show that if I vary the radius of this sphere, that centroid, C0, the average of those points, is independent of the radius. But it's not happening yet because when I move the radius, when I alter the radius, sometimes Mathematica does not correctly report the entire extent of these two components, and also because I suspect there could be some complex solutions happening here as well. Okay, but this just gives you a flavor as to what we can do. For example, let me move the sphere a little bit away from the cone, like so, like so. Now, okay, so Mathematica now is showing the two components correctly, the blue components. They're not planar, and it's also showing their centroid, okay, which is being computed also numerically by Mathematica, that blue point over there. Okay, now the question is, if I just tweak the radius over here, and Mathematica is still reporting the full extent of the components. So here are the coordinates of C0, of the centroid. Okay, so let's go ahead and jog R up. As I jog R up, okay, and I'm back in a, so right now see, I've lost part of that region, but let's see if I can restore it somehow just by tweaking these coordinates of the center of the circle. Yeah, I'm not getting great stability here on, yeah, on those regions. Here we go. Okay, so now I'm losing part of the one below. Yeah, so Mathematica is having trouble. But the question here, you already understand it, right? If I fix a particular center for that sphere, okay, x, y, z, okay, and I compute the two components. Let's see if I can restore them here somehow, so I can make the argument like that. Okay, so now it looks like I lost it completely. Let's try to go back to, yeah, okay, so here we go. So now if I compute the components, and there should be some complex components, can I make the argument that the centroid, that blue point, okay, of both real and complex components is independent of the radius of the circle, and it only depends on the center of that circle? I believe it is, because you can reduce this problem to just, imagine I just had an infinite set of planes, okay, that were perpendicular to the axis of this cone, and I just sliced this image by 1,000 or 1,000,000 planes, and they're all, like, you know, a sandwich of planes perpendicular to the axis of this cone. Now each one of those slices, let's start, you know, at the slice that actually cuts through the sphere, is gonna show on that plane, if you intersect both the sphere and the cone, the same problem as we had before, namely the intersection of a circle with an algebraic curve. In this case, it would be another circle because it would be the intersection of the cone, but you make this cone be any other algebraic surface and you'd get an algebraic plane curve, right? Now, because as I vary the radius of the sphere, I would be varying the radius of the slice of that sphere on that plane, namely the radius of a particular circle, I would go back to the previous argument, where the centroid of intersections of a circle with plane curve does not depend on the center, on the radius of the circle. So because the centroid of the centroids is a linear thing, if you will, the sum of everything, I think it should work. It should work. So I'm doing two things with this video: appreciating the beauty of these intersections. They're non-planar space curves that I can somehow, you know, analyze. You can see here that I'm varying the radius of the circle, of the sphere, and it doesn't look like that blue dot, the numerically computed centroid, is varying in position, which is kind of it's already a first evidence that we might be correct. Okay, so you get the idea. Let me just use the final few seconds here to perhaps show some other classes of intersections. So for example, if I reduce the radius a bit, you can get a single curve. There you go, look at that beauty there. Hang on, right here, yes. Look at that beauty. So now you're getting an intersection, probably because the sphere is just passing through the node or the vertex of that cone. So you're getting this beautiful self-intersected space curve. Okay, it should be the case that its centroid is the same as the one where we're getting two components, all complex solutions taken into account. Let's continue to increase that. So now you can see that it bifurcates. And what if we decrease the radius? Now you get a single component, right? You got a single component. Anyway, you get the flavor of this. And if you have energy to derive some of these space curves algebraically and check if their centroid is fixed with respect to the R of the sphere, I would really appreciate it. See you on the next video.